Okay, thank you very much, Michael, for the introduction. And also thank you, the organizer, for giving me the opportunities to give a talk about my wonderful project of my PhD thesis. So let's get started. So everybody might have a question in mind already once you hear the title of the talk, what is a time crystal? And to give everybody on the same page, I'm going to give a few introduction and also a history of a time crystal, what people are doing. So let's get started. So in physics, it is this question arrived by Frank Wilczek. So he's a Nobel laureate. In 2012, he raised the question, is there a system in nature that spontaneously breaks a time translation symmetry in its ground state in closed system? So really simple, analogous to just solid state crystal where you have like liquid states, and then this translation symmetry is broken, and then it's from a crystal, like from water crystallized into ice, for example. So what is he thinking about? So let me give you this nice picture and summarize. So it has to be like break the symmetry, continuous translation symmetry, then you get a solid, and you see this lattice spacing of A. And you can have to be able to draw a phase diagram, for example, by pressure and temperature. This is a very famous phase diagram from water that you know. So here you see that there's a solid region that you can see the crystal of the ice. And then there's a liquid and then gas, for example. And this phase we have has to be robust. What about time crystal? Everything is really mapped. It's exactly the same, except that now the axis of space mapped into time. So if there's a system that in ground state, it has a continuous time translation symmetry. And once across the phase boundary, this symmetry is broken, such that now every time you have to probe your system, every period A, so then you can probe the same, for example, here, the density of the state. I think, okay. And then we call this a time crystal. And similar thing, we have to be able to draw a phase diagram spanned by what, we don't know yet. And probably this, we find an island called a time crystalline phase, for example. Of course, it has to be robust and this has to be tested. But turns out that not long after his proposal, there's a series of no-go theorem saying that it is impossible in nature, such this spontaneous break of time translation symmetry in ground state and closed system is allowed. But that is not the end of the story. We're still excited and still keep searching for a time crystal because it's such a nice terminology, and then otherwise my talk ends here if everybody stops. Right, okay, you know, there's more. So what is the history of all of this? So 2012 is proposed by Frank Wilczek. This original proposal that you have a closed system drawn by this box and it breaks a continuous time translation symmetry. So this is impossible. And next, what people are trying to find is that they're trying to loosen the constraint a little bit. What if we don't break continuous translation symmetry? Or what if we don't break it in its ground state, but we find a time crystal in a non-equilibrium state, for example? And this gives birth to a new field, which is called searching for a discrete time crystal. So the rule of the game is like this. So whatever type of symmetry you break, you call that a time crystal. So the original proposal would be a continuous time crystal because it breaks a continuous translation symmetry. But here, what people propose is that you don't start with a continuous symmetry in time, but you imprint already some discreteness of your system. For example, you flow K-drive it. So your system Hamiltonian already has a periodicity of B. Then if this discrete translation symmetry is broken, then you end up with another period that your system responds to. And this can be realized such, for example, like a subharmonic response, for example. You drive it with frequency f, but then your system responds with f over 2, for example. And this is a new, excitement. So people try to search for it experimentally. And not long after the proposal, just 1 year in 2017, there's a group from Chris Monroe and Michael Luchin that realized this in the system of spin chains. For example, there's a spin, and then you can think of a spin as a chain of chain of spin, chain of ions, for example. Chain of ions, and you can think of it as a spin chain. And when they drive, and then this chain alignment changes into like left or right. This is the example. And then here also in the Michael-Lukin group is the system of the nitrogen vacancy centers. They can also do the same thing. They drive and then see the subharmonic response. They characterize that this phase is robust. But these are all in the closed system. So there's no energy exchange to the environment, and it is subjected to heating because you drive and then heat distributed to all over your particles. But what can we do? So if you might think about dissipation in your system, you might think that dissipation might kill your lifetime. But here there's a series of theories as well saying that a good dissipation could help prolong the lifetime and stabilize your time crystal. That's why it comes the word dissipative, discrete time crystal. Because now we're not working on a driven closed system anymore, but we have an open system where you can couple to a bus. For example, this system could be a cavity QED, for example, because your cavity can have a finite transmission rate, and then your intra-cavity light leaves to the cavity. And in our group, we first realized this type of dissipative time crystal in open system for the first time in 2021. So as you can see, there was already a first talk of today, if you arrive on time and you listen to the talk. But here we capture it a little bit. But this is not the main goal of this talk, but you have a Bose-Einstein condensate placed inside an optical cavity. Then what we can do is that we can pump it transversely, and then you can drive this pump periodically. So here the message of this slide is that you drive it sinusoidally, and then the observable, what we have here is on the blue curve. So you can see that it oscillates, but at half of the frequency of the drive. And this is what we call is a subharmonic, and then we characterize it and found that we can create a discrete time crystal. But what we can do more, in our open system, in the cavity QED system, we can bring it a bit closer to the original idea. So we don't break discrete, but we instead can break a continuous time translation symmetry. What is different now from the original idea is that now we have an open system instead of a closed system. So now it breaks, you do something to it, and then it starts to oscillate. And then we start to characterize it. And this is the main topic of the talk today. So I will give more into detail about how we can realize this type of a continuous time crystal. So let's introduce you an experimental system, since I'm an experimentalist. Now we have both atom cavity side. So we have a cavity side, we have a ultra high finesse cavity. There's two mirrors here, as you show, placed in that direction. And inside this blue part, we have a Bose-Einstein condensate of the rubidium-87 atoms. So the characteristic of our system is that we have a recoil frequency of your atom, and the field decay rate of your cavity is really evolved in the same footsteps. So it's the same in the kilohertz regime. So what does it mean? It means that your atomic dynamics and your light field dynamics evolve in a really similar footsteps. And what we can do is that we have a pump transversally, as I introduced before, and there's a mirror. So you retroreflect your pump to your BC. And if there is an intra-cavity photons arrive, we'll be able to detect it up here because the cavity can transmit some photons. But we can detect by the heterodyne because we can detect amplitude and the phase of the light fields in there. So here, this is what it's not a BC yet, it's just the cold rubidium gas, as you see inside here in the yellow dot. This is a picture taken by just a mobile phone. And what else would we can do? So this is really an experimental realization of the really first talk of the Dickey superradiant phase transition. So if we start to pump, now your BC is subjected to a standing wave potential. And then we call this phase a normal phase. But once you crank up your pump strength, so it's just the intensity of the pump, then suddenly you see light in the cavity, you see light in the detector, and as well as your atomic density is self-organize itself into such a pattern called the checkerboard pattern. In this pattern, it supports best the scattering from the pump here, and then scattered into the cavity field. And if the atomic is, the displacement is exactly lambda, that means the light scattered from these atoms and the light scattered from this photon is constructively interferes. So then this cavity field can form nicely. How does it look like in the real measurement? So here, x-axis is the time axis. All right. And then we crank up the pump strength. So here's the pump strength, we increase it. So below threshold, there's nothing yet because we don't detect any photons from this detector. And because there's no photons, the phase of the light is undefined. It can go from -pi to pi, whatever, we don't know. But once we cross the threshold, we start to see this increasing of number of photons inside the cavity because the atomic form the grating that looks like this, and it scatters photons into the cavity and amplified. And now the phase of the light is defined, so it's fixed to one phase. That means we are in one of the checkerboard pattern. We don't know. We know that we're in one. So it's a really nice picture from the first talk that in this normal phase, you have such a potential that has one minima. But once across the threshold, you have two new minima, which is degenerate. And this two is realized by these two generate sublattices. We don't know which it is, but we can prove that it has a 50-50 chance to fall into one. What else can we do to probe our system? We can also take an absorption imaging showing the momentum spectra of your atomic section. So below the pump field in a normal phase, it's just a normal BC momentum mainly is in 0, momentum mode with some small peak at a 2h/k. It's 2h/k because k wave vector is equal to 2 pi 1 over lambda. If lambda is half, and then you have x appears 2h/k. And here on the self-organized phase, you see that their peak at ±1 mode appears. And this is showing that it has really a pattern of a checkerboard pattern. So it's done. We are equipped with everything we have in the experimental side. We can detect light field. We can take a picture of the atomic distribution in the momentum space. How can we realize the time crystal now? So what do is like we pump transversely with the pump which is Bluetooth detuned to the atomic transition. So same picture. So we pump, then we take some number of photons. If you see from the plot before I showed, this is just a single slice along y-axis. So then I fix the frequency of the pump. The frequency of the pump is fixed. But now if I would tune the frequency of my pump and then scan my pump strength in x-axis. So before it's just no photons, then I detect some photons, I'm in a self-organized phase, but now I change the frequency and I stack them up. You may see already that there's a region in some frequency that you don't just see photons, it increases, but you see photons. Sometimes it appears, sometimes it's not. So you see this white dot, like white and black, white and black. And this is already show a hint that there's something oscillating in time. If I ramp in my pump, stop at this dot, and then keep my pump strength constant, you would see that the light field that leaking out of the cavity is oscillating with a single really nice frequency. If you do a frequency, Fourier transform of this light field, you would see that you see a really nice sharp frequency at around 9.5 kilohertz. And now I scan do the same protocol all over this yellow grid to probe that where we see best this oscillation. Then we have to quantify how much crystal do we find, how can we quantify it. So from this Fourier transform, we quantify a crystalline fraction. The higher the crystalline fraction, the higher crystal you have. So this is defined by you integrate over the peak around this frequency divided by the power of other frequency in the range, within the range. So then we define this crystalline fraction. And this is how we saw, or what we see. Right. So here, this is plotting in color scale the crystalline fraction. You see that around this frequency of the pump, we see a really nice high density of the crystal fraction in there. And its frequency, we can also map out in here that it ranging between 9 to 10 kilohertz around this frequency. And to rule out where is the time crystal phase or where not, we define it such that if the crystalline fraction is above one threshold, then we rule out that within this phase is a time crystal, the rest is not. And this is how our phase diagram span by the frequency of the pump and the strength of the pump in x-axis. And what next we have to test if it's a really spontaneously breaking of a time translation symmetry. So we have to be able to show that it is really spontaneously break the symmetry. How do we do that? If you think back in real space, in normal crystal, spontaneously breaking means that the first crystal which is formed could happen at any point in space. This has no preference. At the same time as in time crystal, that means the oscillation, if you would do it many, many, many times, it could appear at any time phase. So think about this Mexican hat, for example. Once you're in there and you would fall into a phase transition, there should be no preference of any phase you could have in the end of your states. So what we do is that we do the same measurement, repeat it over 1,500 times. Okay, that's a lot. Even though it has the same frequency of the FFT, you can see that the time phase could be really different by pi, for example. And then we map out what is the distribution of this time phase over this data point. And then you see that it distributes all over angle. So this angle means the time phase. So it's just no preference over all of this time phase. And we can also prove by our theory such that this is really the case, that you can also see it and prove it in theory as well. So yeah, we prove that we see something oscillate. We have some spontaneously breaking of time translation symmetry. Next, we have to test if this phase is robust. So how can we do?
Sorry, can I just ask a question?
Yeah, sure.
To clarify, if it were not broken, would you just have a dot there?
Yeah, you can have a one cluster, like because something happened, you always fall into one phase. So
stroboscopic pictures of
yeah, right. So, okay. Yeah, we test the robustness next. So what can you think about this picture? How robustness could you test your crystal? So we add white noise on one of the axes. This is really analogous to if you would increase the temperature of your ice a little bit or change the temperature or pressure, then you should see that your ice slowly melts. So you have less and less crystalline fraction due to number of your temperature fluctuations, for example. So here what we see is that if we add noise on the strength of the pump, so here we choose white noise, and if we increase it, you see that the crystalline fraction within the peak start to break down. And if you plot what is the fraction within the peak, it slowly melts or like reduce with the noise strength. And this is how we can prove that there's some plateau, that it's robust, and then it slowly melts. So I think, I'm not sure how much time I have. More time, good. So this is a mini summary then. So here I show that I can have a system, an open system, that break time translation symmetry because I did not drive my pump. This is a DC drive, but your system oscillates in time. And we can show that the time phase of this oscillation doesn't prefer any time phase. So it's really spontaneous breaking of this symmetry. And I can show that I have a phase diagram spanned by two parameters, which is the frequency of the pump and the strength of the pump. And I also test that this phase is robust, that I can show the melting nature of this crystal. So here I would like to thank my team. So there's a strong theory collaboration with the group of Professor Ludwig Mathai. Jim Scooter is the PhD student. And we have a collaboration with Jason as well. Now he's a professor in the Philippines. And of course, I'm from the experimental side, my professor Andreas Hemmerich and the PI, the postdoc Hans Kessler. So there it comes with the outlook, if I have time, which I have, right? So here from continuous, I can make it into discrete time crystal as well on the same setup, but now we drive with twice the frequency. So here is just the same picture, but tilted. Oh no, not tilted. We just pump in a different direction. But now my pump has a driving nature. So it's sinusoidal drive with the frequency of omega driving with the strength of F0. And what happened is that we can detect some oscillatory with exactly half of a driven frequency. And we call this a seeding experiment. So what happened is that, so here you ramp your pump strength across the threshold, you see some light, you're in the self-organization phase. And if your frequency is right, you already see some LC, sometimes we call our time crystal limit cycles. Here you see already some oscillatory behavior, but once you start to drive your frequency, here I drive it around 22 kilohertz, which is around twice of the original frequency we observed. And then you see that the frequency is locked exactly to half of the frequency. If you would be able to Fourier transform by eyes, which you're not, now I'll do it for you, that it is really exactly half. So now frequency is locked to half of the modulation. What do we do? So here, without driving, we have this distribution of frequency of your time crystal. So it's really spreading. So it could be anything. But then once you start to drive, you see that it's locked to exactly 0.5 of your driving frequency. So now you can really see it and tell your time crystal which frequency they should oscillate into. And it looks really similar to a seeding of your laser. What you have a seeding, and then you see some, sharp peak exactly at that half of the frequency you have. And now what interesting thing is that from Nina's question, now if we don't drive, we have a 2 pi time phase distribution. Can you guess what will happen to the driven case? Now the time phase is pinned down into only 2 clusters. Because now we have the drive, the frequency could be, because the frequency is half, it could be locked to one of the peak or the other one. So there's only 2 possibilities that the time phase could appear. So we can see really a nice pin down of your time phase of your time crystal. And what else we can do? We can do more. We can study how it looks like in your atomic section. What does it do macroscopically? Why can we get this? So from the seeding experiment, because now the phase is pinned down, we don't have random phase anytime. If we would do the experiment, stop at exactly this time, take a picture of your atomic density. Before you cannot, because the phase could be anything, you would do, 10,000 times to be able to post-select the right time phase and take the right atomic density picture. Now you have only 2. It is easier. You just post-select one of these, stop it at a small step of time, take a picture of your momentum distribution. What you see is that here I zoom in, so the light, the blue is also the light field of your cavity, and the orange one is the momentum distribution. I count the momentum in the ±1 mode, and I plot it in orange. So you see that there's an oscillation as well, like this, in your atomic section. So what does it mean is that sometimes it really aligns itself into a nice self-organization phase, but the light field, not but the light field, and then sometimes not. So that means you sometimes really well localized and not, and well localized again. That's why you see light like dip down and then shooting up again. So here we can really study how it looks like in real time, what oscillates in real space and form this time crystal. So, right, that brings me to the end of my talk, really, for real, because this is just a preliminary data. I was really excited to show you these 2 time phase locking. And then, yeah, I'm happy for any questions.